Part 3, ARM Assembly Language, the 32-bit version. As I've already said, this part is very long, it's very boring. It's, almost this or this instruction works like that, this, and so on and so forth. It's long, it's divided into 4 parts. We start, with the introduction, then we move to the data processing instruction, branching, how to access the memory, and the operation on the stack. But the good thing is that after this part, the things are going to be more interesting. So let's go. So each instruction consists of 2 parts. In this case, we are considering mov r00. The first part is the opcode that indicates the type of operation. In this case is mov. And then the operands, there are the target of our operation, and in this case is R0 and 0. Obviously, different opcodes may have different operand requirements, and this is exactly what we're going to see in this part. For example, if we consider the mov instruction must have exactly 2 arguments. The first one must identify a register, and the second one must provide a register or an immediate. Like in this case, each immediate is prefixed by a sharp. Okay. The semantic of the move instruction, the semantic is, roughly speaking, what is this operation doing? And in this case, I am expressing the semantic of this operation in using a natural language, the English language. I mean, a very error-prone English language, but the semantic of the move means I am moving 0, so the 0 value, into R0. And at the end of this operation, in R0, we will find the 0 value. As I've already said, an immediate is a constant number, okay? And why it's named an immediate? Because it is immediately available at compile time. So when we are giving our source code to the compiler, doesn't matter if it's written in a high level language or in assembly language, the compiler already know this value, and it can put the value directly in the instruction. However, immediates have a problem. The problem comes from the fact that an instruction is 32-bit long, and then among those 32-bit, you need to encode the immediate. So, for example, in this case, as you can see in the example, if you try to create an assembly ARM program with this instruction, the compiler will complain that it can't create such immediate. And for example, in when you're using moving instruction like the mov, you just have 12 bits to encode the immediates. So if your number is bigger than 12 bits, requires more than 12 bits, you have a problem. And also, for example, when you're using branch instruction, some numbers must be multiple of 4. And there are solutions to this problem, but I am telling this to you because sometimes maybe when we are going to write some shellcodes, the compiler will complain that we can't produce some immediates. And the solutions are the following. So when possible, you can convert to a corresponding form. In this case, for example, the example suggests us to negate the result. Or you can use more instructions, to build the constant. Maybe you start with a number, then you subtract something, you use different instructions to get the same value. And finally, you can create a table of immediates, and you can jump, you can refer to this table of immediates, you can craft your number, and then you can access them. Data processing instructions. So first of all, let's learn how to read this notation that is directly taken from the official ARM documentation. So here we have the opcode, that's the operation, and then among the curly brackets we have the optional things. We will see this more in detail in the next slide. and then we have two mandatory operands. So here opcode is one of some, arithmetic operation, addition, subtraction, and then we have bitwise logical operation, and or XOR, and so on and so forth. Then we have shift and rotate operation on the same register. Those instructions are very useful when we are dealing some crypto stuff. And data movement, we have already seen mov, and this is MVN, that means move and negate. Then we have the comparison operation, and the only thing about comparison operation, I don't know if you already know something about x86, but in general, when you're doing an operation, you are often setting some flags. Do you remember that we have in the CPSR register, we have the 0 flag, for example. So when we are comparing two values, if such values are equal, then we will set the 0 flag in the CSPR register. And this is the reason why the comparison instruction, they never specify a destination register. They are always here just to modify the CSPR register according to the result of some operation. Please keep it in mind that data instruction, they do not work in memories, not x86. We cannot take values from memories and modify them. We are just working only on registers. The RD usually is the destination register, so we are doing some operation and the result is gonna be put in this register. And again, operand 1 can be a register, operand 2 is a register, The only point is that operand 2 can be the result of a bit and shift operation or an immediate value. So you remember we have some restriction on the immediate values. So curly brackets means something that is optional, something that can be omitted. In this case, let's start with the S, that is exactly the S character. It means that the CPSR register is updated based on the result of the operation. So if, for example, if you are subtracting two numbers, two equal numbers, and you get a 0, the Z flag will be updated accordingly. And then we also have the condition. We will see them in a few seconds. That it means that this instruction can execute conditionally with respect to the CPRS flag. What does it mean? What means that, for example, if we have a move with some condition, it means that this instruction will be executed according to the result, to the value of some CPSR's flag. Let's see some example. So in this case, we have mov and E. It means that it moves the data only if the Z flag is 0. And this doesn't exist in x86, It's something, I think it's something new for you. Then we have add, then S, and then EQ. It means that you have to perform this addition if the Z flag is 1. And then you have to update the CSPR register with the result. So in this case, we are combining the optional S with the IQ condition flag. So please keep it in mind that this was different in the past, but at the moment to date, you always have to specify the S before the condition code. Here we have the list of all the available condition codes. I don't want to go all over one by one. I think that the one that you find more often are, we have already seen EQ and E not equal. Here we are checking the Z flag condition. Then we have all the, comparison if something is greater than or equal, less than, and, and so on and so forth. Always is the default. You don't have to set this condition for code. This means that the instruction will be always executed. So from now on, for the rest of the course, if you need to remember some, there will be some exercises, and if you need to remember some condition code, you can go back and you can go to this slide and have a look what some condition code means, or which one do you want to use. We have the classical arithmetic instruction. We can add and we can subtract. The difference between adding or subtracting with carry, so the difference between add ADC and sub SBC, it means that we are performing the sum or the subtraction, and we are considering the carry bit. So if the carry bit is set, we are subtracting or summing the value of the carry bit. So if it is set to 1, we are summing or subtracting 1. If it's set to 0, basically we are doing nothing. Then we have also the reverse subtract, because with the subtract we are subtracting our n minus the operand 2. On the other hand, we are subtracting operand 2 minus operand Rn. Please keep it in mind that if operand 1 is the same as Rd, it can be omitted. I have seen a lot of the compilers writing in this form that it means that please subtract R0, add R0 and R1, and the result, please put the result in R0. And it's an equivalent form. Then we have the obvious logical instruction, we have the logical AND, we have the logical OR bit set. What does it mean? If you think about it for a moment, also if you take a pen and paper, all the bits that you're going to set to 1 in operand 2, they are going to be set also in Rd. We will see another instruction in a few seconds. Then we have, the XOR, and then we have, this one, the BAC, the logical and the not that stays for bit clear. This is the opposite. All the bits that you're going to set in operand 1 will be set to 0 in the Rd, in the destination register. Take some number, take pen and paper and practice it. You will see in a few seconds what does it mean, what I'm going to say. And finally, we have the logical or not. So, nothing strange here. Then we have the data movement instruction. We have already seen move. We are taking the value, the number that is in operand 2, and we are putting it into the Rd. Then we have the move not. We are negating the number, the logical negation, bitwise logical negation of the operand 2. We are putting it into the destination register. And please keep it in mind, and this happens very often. You can also update the CSPR flags according to the results. So at the end of the instruction, you take the number that you have in Rd, and if, for example, if it is 0, the CPU is going to set the Z flag in the CSPR. So maybe you have already noticed that in this way you can perform a branch instruction using the move. So the PC is the program counter is inside the PC. We have the address that is pointing to the memory region that contains our code. So what can we do? You can say, hey, please change the value of the program counter to this number, that to this number. But it is possible. You can do that. This is totally different from x86. In x86 you don't have this direct control over the PC, but obviously ARM strongly recommends to don't use this instruction. Instead you have to use the BX or BLX instruction that we will discuss later, that they are very useful for software for portability. Okay, finally we have enough knowledge to see a very first simple example. What we're going to do here, we are taking this simple snippet in C, and we're going to translate this program into ARM assembly. And you will see this problem very often when we are dealing with the compiler. So the compiler is a tool, is something that is able to translate some assembly code is trying to translate it back to a high level language like C, for example. The problem is that the mapping from some snippet in C to the corresponding assembly instruction is not unique. So maybe we take this snippet, we compile the snippet, and then using a decompiler, we try to get this snippet back, but it is very likely that is not going to happen. So what we're going to see here is a possible translation of this source code. So in a few words, what we're going to do here, we are setting the total variable to 0, then the a variable to 10, and we are iterating this loop while a is greater than 10, and we are adding the value of a to total on each step, and we are decrementing a on each step. So what will happen here, we will start the total will start to be set to 10, and then we are doing 10 plus 9 plus 8 blah 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 and so on and so forth. So let's see one possible solution. Okay, we have decided to this is, and this is the reason why this is one of the possible solutions. I have decided to use R0 as the total variable. Maybe ZCC would have used another register. So we start moving 0 to R0, and we put 10 into R1. So R1 will be our A variable. Then we are adding R1 to R0, and you are setting the result into R0. If you remember, we can omit, given the fact that those registers are the same, we can just write add R0, R1. Okay, another thing that I wanna, on which I wanna focus your attention are those strings. They are labels. They just exist in the assembly language word. When you on the binary, you will just see numbers, just addresses. And what's the purpose of this label? We will use this label here, okay? Don't worry, we will see what does it mean in a few seconds. B is another instruction that you haven't already seen. B means branch. So what's going on here, that if this condition gt greater than, if this condition is true, we are going to jump to this label. So we are performing those operations, and if this condition is satisfied, we will jump back to this instruction. And I mean, you can see this this in action with this infinite loop. We are doing, hey, branch to the halt label. The halt label is here. So we are always performing this operation. So we were doing this operation, then we are doing this. We are subtracting 1 to the value that's stored in R1, and we are setting the results back in R1. Again, this could have been written like subs R1, 1, omitting this register. But here we are using the S. What does it mean? It means, hey, please update the CSPR flags accordingly to this result. And what we are interested here, we want to check if if we are going to set the Z flag to 1, because if the Z flag is 1, it means that we got a 0 result, and here we have to stop if we reach the 0. So what does it mean here is that, okay, perform those actions, update the CSPR register accordingly, and then if such condition holds, especially if we don't have a 0 result from the ALU, jump to this instruction here. So this is our for loop. In the end, if this condition is no more true, jump, continue to this instruction that is, it is an infinite loop. Okay, shift and rotate instructions. So we have the logical shift left and logical shift right, that if you think about it, if you take a number in its binary format and you are, shifting the bits from one side or another, we are multiplying or dividing by 2 to the power of n. Pen and paper and try it by yourself. Then you have the rotate right, and then we have the arithmetical shift right. We will see how it works in the next slide, but please keep it in mind that those instructions, they do not exist in reality. The point is that the assembler will encode them by using the move instructions, but I am telling it to you because some disassembler will just show the pseudo instruction. And for example, in this case, if we want to perform a logical shift left on the value inside R0, this will be implemented using the move instruction. But how is it possible? We will see this more in detail in the rest of this part. But here we are taking full advantage of the ARM architecture. We are performing this shift. Do you remember this image? We are performing this shift using the shifter. So before putting the result in to the ALU, we are shifting the result. Let's see some examples. So here we are logical shifting by 4 to the left, here by right. So on the first example, we were multiplying by 2 to the power of n. In this latter case, we are dividing. And then we have the rotate right. We are moving the bits by 4 positions. And then here we have the arithmetic shift right by 4 with a positive value. You remember, go back one slide, okay? This is considered arithmetic shift right signed division, It means that we are considering the sign of this number. So in this case, when we are dealing with a positive number, we are, just maintaining the 0 because this is a positive value. Instead, in this case, the most significant bit is set to 1, so this means that this is a negative value, and so we need to maintain to still keep track of the fact that this is a negative number. This is due to the fact that the numbers, the negative integer numbers at this level, at this binary level, they are written using the choose complement. If you don't know what I'm talking about, just refer to the Wikipedia webpage that is extremely well written, and you will understand more in detail what I'm talking about, and maybe take pen and paper and try to see this by yourself. Also try to understand why this is considered the signed division by 4. Okay, as we have just seen, operand 2 can be shifted before data processing as the part of the same instruction. So we have seen one of its 3 forms when we are taking an immediate value. For example, we are moving 42 in the value 42 in the number R0, and then we are going to see how registers can be shifted by values. So we are taking the value in R2, we are logically shifting by 1 bit, and then we are writing back the result in R2. Or, okay, we are going to see that even if ARM instructions are considered simple, maybe they are simple as an instruction, they are simple to implement, they require slow cycles. It doesn't mean that they are simple to understand, they can be quite complex, quite tricky. We can add the S, the condition flags. Now we are going to see some a bit more complicated examples. So R as B, you remember, is a reverse subtract. And what we're going to do here, let's start from the right. We are taking the value in R14 and we are performing an arithmetic shift right of 14 bits. Then the result, okay, is then subtracted to the value that's contained in R5, and then we are writing back this result in R10. Then we can also shift registers by registers. So for example, big, is the logical and not, also named bit clear. We are logical shifting R1 by the number of bits contained in R0. Then we're writing back the result in, and then this result will be negated, and we will perform an AND with R11, and then all of this stuff we will write back again to the R11 register. We can also combine it with the compare instruction. So for example, we are rotating the value in R8 by the number of bits contained in R0, and then we're writing and then we are comparing this number with the number compared in R9, and we in this case the compare instruction is not moving data somewhere, is just used to set the CPRS flag. Okay, let's see some example, but that you will also find it in the real world. So as we said before, here we are multiplying R0 by 2 to the power of 1, so we are multiplying R0 by 2. Here we are dividing by 4, 2 times 2 to the power of 2, it's 4. And then it's the same, the difference that here we are using the arithmetic shift right that will take care of respecting the bit sign. Then here we are, rotating right by 16, okay, R3, and we are writing back it to R3. So what we are doing here, we are rotating, and in practice we are swapping the top and the bottom halves of R3. Then, okay, this is quite tricky. Here we are taking R4 and we are performing a logical shift left of 4 position. 2 power of 4 is 16, and what does it mean here is that we are summing R4 plus R4 16 times. What does it mean? That we are multiplying R4 by 17, because n times 17, so you can also write it as 16 plus 1, and this is basic math. It is the same like writing n times 16 plus n. So what are we doing here? Here we are multiplying R4 16 times, and then we are adding R4, and you're writing back the result. Again, this is the same trick. This time we are subtracting. So here we are performing a logical shift left of 5. So here we are multiplying by 32, and then we are subtracting R5. And this is the same as multiplying R5 by 31. Here's the same catch, you can write 31 as 32 minus 1, basic math, and again, it is the same as here. Okay, final example. This is, quite strange, because here we have a value but without the sharp, and this specific way of writing an instruction, it means that the ROR operation is implied. So here, this means that we have 1, and we are rotating right by 20 position the bit in the first in the least significant byte, and 1 ROR 20 corresponds to 0x1000. let's see this, you know, that basically what does it mean is that we are here, we are getting 0x1000, and we are putting this, we are summing the previous value that was stored in R12. We are basically summing this number. Let's see, you know, very fast. Okay, here we have 1 here, and we are shifting, let's not shifting, rotating by 20 position. So here we have the 32 bits. We go here 4, 8, 12, 16, 17, 18, 9, 20. Okay, we have shifted this bit, and you see we got 1000 in hexadecimal. Comparison instructions are the instruction on which the S is always implied. It means that they always update the CPRS flags, but they do not write the result back to some register. So the opcode can be one of CMP, that stands for compare, that is exactly the same as sub S, you know, subtracting with the S, with the only difference is that we do not write back the result to some register. Then we have the CMN, that instead is we are adding, you know, Rn with operand 2. Then we have TST, in this case we are performing a logical AND. And finally we got the TEQ, that stands for test equivalence, that is corresponds to the you know, XOR. Okay, easy. Branching instructions, we have already seen a branch instruction, we have already seen the B instruction in that example in which we were trying to convert some simple NIP-C program into the corresponding ARM assembly 1, and we found that this instruction is just putting the value of the label into the program counter. That is, you know, this is the register that is in charge of pointing to the instruction that is gonna executed. What else? Yes, we have also the branch with link instruction. That is the same. The only difference is that it is saving the link, it is saving the address of the next instruction into the link register, and then it is performing the jump. But what does it mean? Why this is helpful? Because when you want to invoke a function and you use a branch with link, you will know at what is the right return address when you are, and where you ended up with your function. We will see this more in detail. There is a dedicated part in this course, but keep it in mind that the branch with link instruction is actually performing 2 actions. As you can see here, okay, there is this optional X. X stays for exchange, okay? So we have the BX and the BLX instruction, and they also work with registers. What does it mean? That you can't write BR0, is not a valid instruction, but you can write BXR0. But the most important feature of the X version is not this one, is the fact that a BX or a BLX instruction is able to switch from ARM to thumb and vice versa, and is able to do that by checking the least significant bit of the label or the register. So if the LSB is 0, it means, hey, I wanna go and I wanna use the ARM mode. If it's set to 1, I wanna use the thumb mode. And this is one of the reasons why alignment is so important. It depends on the fact that you can't jump, you can't branch to an address that is odd, that is that the least significant bit is 0, because when you now I will explain this fact in 1 second, because when you want to switch, for example, from ARM to thumb, what you can do is that, okay, take the program counter, add 1, so we are setting the LSB to 1, and then we are moving back the result to 0. And then we are saying, okay, branch to R0. So we are literally saying go to the next instruction, but then switch to thumb mode. And this is happening, but the branch instruction is always ignoring the LSB, you know? And this is the reason why alignment is important, because the LSB is always discarded and all the instruction must always be aligned modulo 2 or modulo 4 if you are in thumb or if you are in ARM. Let's see some summary example in which I will show you how ARM instruction powerful can be. So let's start with this statement, and we are checking if a is equal to 0. We will branch to the function func with argument 1. Then if a is equal to 0, we also set x to 0. If a is greater than 0, we set to 1. And last statement, if a is equal to 4 or a is equal to 10, we will set x equal to 0. Let's see one possible solution. Here we have, we assume that our variable a is mapped into R0. Here we are comparing 0 with R0, and you remember CMP, we are subtracting 0 from R0 and we are updating the CPSR register accordingly. And then if AQ, you remember, is a condition code that will check the Z flag. So AQ stays for equals 0, okay? So if the result of the previous instruction, if the Z bit of the CPSR register is set, we move 1 to R0, and then we will call the function func again if the Z flag is set. This is a little preview of the AAPCS, the ARM procedure calling standard. That means that the first argument to a function is passed into R0. Then we compare a with 0, and if it is equal, you see, we set it to 1. If it is greater than, we set to 1. Sorry, if it's equal, we set to 0. If it's greater than, we set to 1. And here, look how an OR condition is checked. You know, first we check if it is equal to 1, but if it is not equal, because it is XOR, you know, it's the name of this way of checking the OR is a tilting OR. It means that we first check this, and if this is true, we don't need to check it. And this is exactly what we're going to do now. We check first that if a is equal to 4, and if it is not equal, we check if it is equal to 10. Otherwise, doesn't matter, you know. We just move this if it is equal. If the previous compare, doesn't matter if this or this one were equal, if we subtracted two numbers that they were the same. Have you ever heard about the Collatz conjecture? Let's have a look at the Let's have a look at the Wikipedia page. Okay, it is a conjecture in math that concerns a sequence defined as follows. You start with any positive integer n, and then each term is obtained from the previous one in the following rules. If the previous term is even, the next term is 1/2 of the previous term here. So if it's odd, else it's even, you divide it by 2. If the previous term is odd, the next term is 3 times the previous term plus 1. So 3 times plus 1. So the Collatz conjecture is still unsolved, and now it's up to you. You have to solve this conjecture. No, I'm kidding. What are we going to do here? We are going to implement this a possible solution starting with n equals to 5. We will see a possible solution in ARM. So, you know, just very fast, we start with 5, okay? Is n different from 1? Yes, it is. It's 5. It's even. So 15 plus 1 is 16. So now n is 16. Is n different from 16? Yes. From 1? Yes, it is. It's 16. So we go to the half. The half of 16 is 8. And then 8 is even, 4, 2, and then we got 1, and we are done. Here the e variable, we are just using this e just to count the number of interaction. So let's see a possible solution. So we use R0 for n and R1 for 0, okay, you see? And so we start with 5 in R0 and 0 into R1. Then very first simple instruction, we add 1 to R1, super easy, and then we need to check if R0, if n is odd or even. So what we are going here, we are using the TST instruction. The TST, you remember, it's used to perform a logical AND between, in this case, between this register and the value, the number 1, that is, number 1 is just, you have just the least significant bit set to 1, so we are just checking the value of the least significant bit of R0. And if this bit is set to 1, it means that is odd. If it's set to 0, it means that it's even. In fact, then the following instruction is branch if EQ. And EQ stays for, is checking if we got a 0 flag in the ALU. So 0 means that it's even, because the least significant bit is set to 0. So if it's 0, we branch to the even label. Okay. Let's branch. Okay. If it is even, what we are going to do here, we are moving R0, the value containing R0, shifted right by 1. So you remember the logical, if you're shifting right by 1 bit, you are dividing by 2 to the power of n, then in this case 2 to the power of 1. So we are shifting by 1, we are dividing by 1, and this is exactly this operation, and we are setting back the result to R0. Then we are comparing if we got 1 in R0, if it is the case, if it is if it is not the case, so if it is not equal, we are checking this in this condition code is checking the Z flag. And if the Z flag is not true, we are branching to the again label. Otherwise, we ends up in this infinite loop. Okay, remaining part is this one. So this condition is not true. And then what we are doing here, you remember the trick. We are logical shifting left by 1. So we are multiplying by 2 to the, we are multiplying R0 times 2 to the power of 1. So it's true. So this operation, it means that we are multiplying R0 by 2. And then we are adding 1. So it is R0 plus 2R0, that stays for free R0. So it's basically this operation, free n. And then we are adding 1. So we are using those instructions, to perform this operation. Then if it's not the case, we branch to the again label, and so on and so forth. But let's see this more in detail, trying to debug this code and see in practice, in reality, what's going to happen. Okay, I already did something for you. I have already started the REVM. I have already started the QEMU emulator. So here I connected to the Raspberry instance, and this is the content of the Hailstone file that we're going to debug. Then I have assembled and linked the file so that we can, the source, so we have produced a runnable executable, and then I'm going to debug it with GDB. First thing, I'm going to set up a breakpoint to the start label so that when I run this program, okay, the program will stop the execution at the very beginning of the start label. So N A, that stays for next instruction, zack, and you see we have executed this instruction. We have set 5 into R0. Then if you press again enter, you are repeating the last command, and so we moved 0 into R1. I mean, R1 was already 0, so no need to do that. Okay, now we are adding R1 to 1. You see, luckily Jeff is highlighting the registry that is going to change, and now we're testing the value of R0, and if we got an 1, okay, we didn't get a 0 result from the ALU. You see, reason not 0. We are not taking this branch, we are not performing this jump because we didn't got a 0 result from the ALU. So this number is odd. So we are doing, you remember the trick, the logical shift left. So in this case, we are multiplying 3 times 5. And yes, here we got 15. Then we're summing 1, so we end up with 10. I mean, it's, 10 is in hex, it is 16 in decimal. Then we are branching, to the, again, same thing, you remember, this is the second interaction, but this time we are taking the branch because we got a 0 flag set because our 0 is even, and we got a 0 result in the ALU. Again, we are shifting our 0 here 1 bit, so we are dividing. So from 10 we got 8, it means from 16 in decimal we got 8 in decimal. We are comparing our 0 with 1. Okay, you see here the carry flag, we did a subtraction, okay, but carry is not borrow. So if the carry flag is set, it means that we didn't need borrow, and it means that this operation was successful. This is not an error. So again, we are not taking the branch because we didn't got a negative result in the ALU. So no, sorry, an E means not equal, so we are checking the value of Z. So the 0 flag is not set, so we are branching to the gain. And again, the same stuff, we are adding one new interaction. We are testing the last significant bit of R0. Okay, it's even. 4. I'm gonna continue. This is the fourth interaction. 2. Again, we are dividing. 1 step and 1. At this point, when we compare R0 with 1, we got a 0 result in the ALU. And in this time, we do not take this branch. We go directly to the alt. This is an infinite loop. This will continue forever. And we are done. Maybe try to repeat this process by yourself. Maybe, try to change the value of R0 and try with a different number. And if you have time, you can always try to solve the Collatz conjecture. Debug time done. Oh, I have a task for you. So please translate this C code into ARM assembly. This is the Euclid's GCD algorithm. You have to use X and Y to 40 and 25. Use R0 for X and R1 for Y. So stop the video, take your time, don't look at the solutions, and I'm waiting for you. Did you watch the solution? Okay, here we go. I'm gonna present a possible solution in 3, 2, 1, go. Okay, as I've already said, x are 0, y are 1. First of all, we perform this comparison, okay? So we are comparing x with y. Then, if x is greater than x, we subtract um, y from x and vice versa. So we are taking advantage of the zt and le greater than and less or equal. And if it's greater than, we are subtracting r1 from r0. On the other hand, we are subtracting r0 from r1. And then if they are not equal, so this is the condition for this loop. If it's not equal, we branch to the again, and so on and so forth. And then we hop. So it doesn't imply that this is the correct solution. This is one of the possible solution. I have another task for you. You have this C code, and inside this C code, we have this mystery function that is a function written in ARM assembly. So here you have the mystery function, and when you call the mystery function with the nth character of the string, you will end up having R0. R0 will contain the nth character of the string. Okay, so here we go. We have this string, hello world. Okay, this is the length of the string, no particular tricks here. Okay, and then here we are allocating a new array, new string of the same length of the string. So what we are going to do here, looks like that probably we are going to copy the string str, performing some modification one at a time of each of its characters, and then we are printing the new string. So my question is, what is this program going to print to the screen? I'm waiting for you. Don't look at the solution. I'm waiting 5 seconds, and then I will explain the solution. 1, 2, 3, 4, and 5. The answer to my question is that this program is printing hello world with the H and W lowercase, because this mystery function is what is actually converting each uppercase character into its lowercase character counterpart. How is it working? Is taking advantage of how characters are encoded, and this case is the ASCII encoding table you see here. So first we have uppercase characters, then we have the lowercase one, you see, and then in this case what we're going to do is we are subtracting the value of the uppercase A to our character in input. We are storing this value and we are checking if this value is within this range. It means if that this character is uppercase. If it is uppercase, we are going to sum the delta from lowercase a to uppercase a. Let's see an example. So we have verified, and our character ends up in this range. So it means that, for example, we got an M that is 0x4d. We're okay, plus, and then we are summing the difference from lowercase a 0x61 minus 0x41. So we are subtracting this offset, and what we got here run is 6d, that you see is the lowercase m. Maybe you have noticed that here we are not checking this number can, we can get to 0, but we are using an unassigned int. So this type coercion allows us to use a single comparison without using the comparison to 0. The ARM code is super easy, with R0 we subtract the value of uppercase A, we compare it with this offset that is a fixed offset, and if this comparison, if t is lower or the same ls lower or same, we add the 0x20 and we return. Easy. Task 3. Write an ARM assembly program that is able to compute the factorial of an input number n. So please don't look at the solution, don't disassemble your C code. We assume that n is already greater than 0, so don't check anything about n. N is greater than 0. N is stored into R0 when you start your program, and you can use R1 for the loop counter. Some examples. So the factorial of 5 is 5 times 4, 3, 2, 1, and 7, 7, 6, and 5 factorial, and so on and so forth. It's the math behind it, it's very, very easy. So I'm gonna count to 5. You have time, so you have time to stop the video, and then I will discuss the solution with you. 5, 4, 3, 2, 1. Okay, we start with the n stored in R0. So we move R0 into R1 and we set all the flags accordingly. What we're going to check here, we want to check if for some reasons R1 is equal to 0. If it is the case, we set R0 with 1, and then look at this condition, we are basically falling through the last condition and we end up in the infinite loop. So what we're going to do here, if R1 is not equal to 0, so basically if the Z flag is not set, what we're going to do here, we are subtracting R1 from 1, we are putting the result again back in R1 in our counter, and we use the S. So we are setting the flag accordingly. At this point, the CPSR flags are modified, and then we are going to multiply if R1 is again not equal, is not 0. And what we are doing here, we are putting into R0 times R and multiplied by R1. And here we go again. If they are not equal, we go back to the loop. So here, the last condition will be when we are subtracting, we do 1 minus 1, we got a 0. And when we got a 0 here, we are not executing this instruction, not even this one, and we ended up with this loop. Done. Memory access instructions are the only instructions that are capable of fetching some value from the memory and putting it in some register. So we have the opcode, and we also have to set the size. So how many bits are we going to transfer or store into memory, the condition, the destination register, and the address in memory. So we have the loader LDR, that it means take some value in memory at some particular address and put it into RD. And then we have the store that is doing the opposite, so from the destination register to some value in memory. The size here can be byte or signed byte, that it means that this operation is going to 0 or sign extend to 32 bits. It means that you are copying some bits and then you are filling the remaining register with 0 or with sign. H for half word, so 16 bits, and when it's omitted, it's on default on word, so 32 bits on ARM32. Let's see such instructions in action with a very simple example that adds all the integers within an array. We start with R0 that contains the address of the first integer within the array. R1 contains the array length, and R4 will contain the sum of all the integers in the array. So this is the code. We start with 4 set to 0, the sum starts to 0, and then here we got the LDR instruction. We use the brackets, it's for the referencing, like x86, it means please take the value at the address containing R0 and put it into R2. Then we are summing R4 with R2. Then we add 4 to R0. It means that we are moving to the next byte, okay, in memory, and then we are subtracting 1. So we have the array length, we are on each interaction, we are subtracting 1 to the array length until we are done here, okay? So, and if the condition is, if R1 is different from 0, again, we go to the add loop. So, then we have the direct that we have seen a couple of seconds ago. So, LDR, we are loading into R0 the value pointed at some address in memory. I mean, R1 is not involved, so no changes to R1. Then we have the indexed base. Again, we have seen it in the previous slide. So we are taking the value at R1. At the end of the computation, R1 is always R1. Now, pre-indexed with base with displacement. So here we have R1, 4, and this means that we are summing R1 plus 4. This is the resulting address in memory. At the end of the computation, R1 is always R1. And then we have pre-indexed, auto-indexing. It means that just by adding this exclamation mark, it means that at the end of the computation, the processor will update R1 with the value of R1 plus 4, so the value that is calculated here. Then we have the post-indexing auto-indexed. It means that we fetch the value from R1, but after we are going to update R1 with the value of R1 plus 4. This is different, you know, we are always updating R1, but the address is different. Then we have the double reg and direct, and as I've already said, here the default is the sum, you know, and here we're taking the value R1 plus R2. For example, if we have added an exclamation mark here, we will end up with, you know, updating the value of R1. But we can also perform, you know, some shifting. So again, what you're doing here we are logical shifting left R2. So we are multiplying R2 by 2 to the power of 3, and then we are summing it to R1. And finally, we have the program counter relative, you know, that is exactly the same as this one, but this is particular because the register here that we are referring to is the program counter, and we will see how it works, how this is useful in the next slide. Addresses can be represented as PC relative expression, so the program counter plus minus the offset. And the good thing is that we can, using this way of addressing memory, it means that it's position independent code in memory, because we just need to know the offset between the data that we need and our program counter, and we can get position independent code, that is code that can be loaded anywhere in memory without the need of adjusting any addresses, you know. So we can take this code, put it whenever we want in memory, and this code will work. So I don't know if you remember this detail. At the beginning of this course, when I was introducing the architecture, I told you that the value of the program counter is always 2 instructions ahead. So in ARM32 it's 8 bytes ahead, and in thumb it's 4 bytes. There are subtle details. Usually it's 4 bytes, but please refer to the official documentation. If you end up in some such case, the point is that luckily these assemblers, they are aware of those facts and they will adjust the things for you. So let's see an example. So in this case, we want to load into R0 the value pointed from the program counter to 16. So here we got the program counter. So this is the 74 is the address of this instruction, but in reality the program counter is ahead of 8 bytes. So in reality at this point the program counter is at 7, the 7C address. Then what we are telling is, hey, take the value pointed by PC plus 16. So PC plus 16 is next, and we end up with this number, and we are going to load this value in memory. But what we have seen so far, it allows us to load a single word, half word or byte in one single operation. Maybe we need, to load several values into memory using the same instruction. And here comes the LDM or STM instruction that allow us to load multiple values in different registers. Here we set the mode that controls how Rn is incremented, because we will have, a registry that points to the beginning of the value address of the value in memory, and then here we have the register list. So the mode controls how Rn is incremented. We can increment after, before, decrement after, or decrement before. We will see everything more in detail in the next slides. Then the exclamation mark tells to the instruction, hey, please update the Rn value at the end of the operation with the latest address that it has been calculated. And then the reg list is a comma separated list, or Rx-Ry style range. We will see this in the next slide more in detail with some examples. Example 1, LDM increment after R0, F0 exclamation mark, so updated at the end of the computation, R5 to R8. This is a range. So the ARM processor will look into the R0 register for an address, and it will load into R5 the 4 bytes starting from R0. Then the 4 bytes from R0 plus 4, 8, and C into R8. At the end of the computation, R0 is updated, and it is updated, and it will be stepped forward by 16 bits. Then, example 2 and 3, LDM increment after R0, R3, R7. This is a comma, okay? Is not a range like that. It is a comma. So it means that the ARM processor will load words addressed by R0 into R3, and then R0 plus 4 bits 4 bytes into R7, and it increments after each load. And then the final result is written back into R0. Example 3, this is a bit more complicated. Here we have a range, here we have a single register, here we have a range, but this could also be written using a comma, because 11 and 12, you know, they are contiguous, they are in sequence, and this instruction will load 7 words from memory, starting from 0 and increment after each load. So R0, R into R1, we will load R0 plus 4, an offset from plus 4 bytes, 8, and so on and so forth. It will increment after it load, but please keep it in mind that when you write an instruction like that, the order of the register is not significant. So writing in this way or in the other way back, you know, it doesn't matter. The final result, the final instruction that is going to be generated is this one. Example number 4, we want to shift every number of an array into the next spot, and the first element will be replaced by a 0. So again, this is a very dumb code. It only works if the array's length is multiple of 4, you know. It is just an example. In R0, we have the address of the first integer in the array. So the address that is pointing to the very first element. R1 is the array length, and as I already said, this code only works if the array length is multiple of 4. So we start and we set 0 into R4. 0 will be this number. Then we are loading, okay, and incrementing after the value pointing to R0, so the first integer in the array, and we are moving the data into R5, R6, R7, and R8. So we are transferring 4 words into 4 different registers. And then what we're going to do, we are storing such values starting from R0, but this time we start from R4, 5, 6, and 7. So R4 was 0. So with this instruction, what we are going to do, we are going to copy in the new array 0, 1, and 2. Not in the new array, sorry. In the old array, we are just replacing those numbers. So at the end of this instruction, we have 0, 1, 2, and 3. 4 is already pending. 4 is in R8. So we move back R8 into R4. We subtract 4 bytes from R1, and then we start again. Stack operations is the last part of part 3. In this subsection, we will discuss all the instructions that help manage the stack. So the stack is the data structures that help manage the active functions that exist in a certain moment during the execution of a program. So what does it mean? An active subroutine, an active function, is a function that has been called, but still it needs to complete its execution. And at the end of the execution, there must exist a system, a strategy, an algorithm that is able to return the control back to the exact point in which the function has been called. So such activation may be nested, so we need a stack structure, so we always need to keep track which is the last function that has been called, the currently active subroutine, that is the routine at the top of the stack. And the stack also must keep track of the point to which each active subroutine must or should return control. Let's see an example. Here you have the function draw line, and here we have the function draw square, that inside its code it is calling the function draw line. What happens when we reach this line of code and we call the draw line function and we are ending up here? So this is the routine at the top of the stack. So this is the top of the stacks. This is, here we have the local variables of draw line. At the moment here we have nothing. The return address, that it will be exactly this point after the draw line. So after the end of the execution of draw line, we must give back the control, we must change the flow, we must return here after the first invocation. And then we have the parameters of draw line, x, x1, y1, and so on and so forth. So this is the stack frame of the draw line subroutine. The stack pointer is always pointing at the top of the stack. Instead, the frame pointer is an address in memory that is used, you know, as a pointer. And we know that after the frame pointer, we have the local variables, okay? And before the same pointer, we have first the return address and then the draw line, the parameters of the function. So instead, at this point here, this is the stack frame from the draw square subroutine, but given the fact that we called the draw line function, we pushed all the parameters and the return addresses on the return address on the stack, and so it is the stack frame of draw square stays under the stack frame of draw line. Here we have the locals of draw line, with here is no one at the moment, the return address of draw line, and then the parameters of draw square. So here we will have x, y, and side. Okay, this was just, you know, a very first introduction. We will see more details later. A stack can be implemented into several ways, into ascending address or descending addresses. The stack pointer can point to the topmost item or to the next free item, so full or empty. And you know, the fact that we are using ARM32 as the stack pointer is just a convention. So other registers can be used, but you know, in the end, all the, you know, the stack is very often implemented in a full descending ways. What does it mean? It means that first of all, the stack pointer, we always use ARM32, and it always points to the topmost item of the stack, and the stack grows downwards. So for this reason, there exist the push and pop pseudo instructions that corresponds to STMDB, that stays, you remember, stays for store multiple decrement before. Because when you push, when you store something, you are moving downwards. Instead, when you're popping, you are incrementing after, so you're going upwards. And you know, also STMFD and LDMFD are pseudo instruction. All of them are pseudo instruction. Those are the real instruction that we have already seen. But in the end, what is the most common use case, the most common instruction that is used when dealing with the stack is STMDB, LDMIA, and we have the pseudo instructions push and pop. So we have the push and the pop instruction with, you know, condition, and then the register list, you know, because you remember, in the end, they are a store and a load instruction. So in both push and pop, the highest number register uses the highest memory address. Then at the end of the execution, the stack pointer is updated accordingly, and if A pop instructions, includes the program counter at the very end, you know, a branch to this location is performed when the pop instruction has completed. And if the reason why we have this behavior, because usually when we want to return, when you are closing a subroutine, when you're ending a subroutine, here we have the return address. So we are popping, and then we want to pop the last element of the stack, the return address. We wanna pop it and wanna put into the program counter in order to branch to the location on which the function were called before. Let's see an example. So here we have push R4, R7, that is equivalent to store multiple for descending R13, so the stack pointer. So at the end of the operation, the stack pointer will be updated with the final value. So you see here, this is the initial stack pointer that is pointing to this element. We are pushing R7, 6, 5, and R4, and at the end of this instruction, the stack pointer will point here. So remember, keep it in mind, as I said before, the highest number register uses the highest number memory address. So the highest register here is R7. So we start from R7 and we end up to the value contained in R4. Then here we have the pop. So what we are going here, we start, stack grows in descending address in memory. So here what we are going to do here, the initial R13 is here. We are popping values. So we start from R4 and then R4, 5, 6, and 7. And at the end of this pop instruction, we'd end up with the stack pointer here and will all such values in the corresponding R4, 5, 6, 7 registry. Okay, it's debug time. Let's debug a simple assembly program that is going to execute some operation on the stack. View EMU emulator with the Raspberry Pi. I have connected in SSH through SSH, and this is the content of the stack basic assembly file. Here we are moving, 0 into R0, 1 into R1, and so on and so forth, R10 into R10. Then we are pushing R10. Then we are pushing those registers. Then we are popping them. We will see that we are restoring their addresses. We will see how the stack evolves, modifies. And then, finally, we push the program counter. That you remember that the program counter is always 8 bytes ahead. So what we are going to do, we load the stack point, we load the element, the top of the stack into R0. That is our saved program counter. We subtract 8 bytes, then we store it back on the top of the stack, and then we pop the first element of the stack into the program counter. So we are branching at this instruction. So this is just an infinite loop. I have already started GDB because it's quite slow. I'm just putting a breakpoint start label. Okay, I'm gonna run it. Okay, perfect. Okay, so yeah, now we do an E, next instruction. 1, 2, 3, stop. Okay, as you can see, we have 1, 2, 3, 4, 5, 6 in those 6 registers. Okay, then and 10 in R10. Then we are pushing R10 back. You see here, first element of the stack is A10. And you see here that the numbers are growing in descending orders, So we are now we are pushing R0, R2, R3, R5, R6. You remember the highest register to the highest memory address. So after this instruction, you will see here highest memory address are 6, 4, 3, 2, and 0. Okay? Then we pop them and we restore them back on the stack. So, no red signs here because nothing changed. Now we push the program counter onto the stack. And here you see that we saved 188, but those instruction was 180. So this confirms that the program counter is always 8 bytes ahead from the current instruction. Now we are loading this number into R0 here. Okay, you see it's in red. This arrow is a feature of Jeff, that is the telescoping. It means that, oh yes, but I have found that this number can be an address and is pointing to something into memory. And you see here the legend is this code. This red means code. It means that this address is pointing somewhere in the code, and you look, it is pointing to this instruction. So what we're going to do now, we are subtracting 8 bytes. So stack, you see, we removed 8 bytes, and Jeff is telling us that this address is pointing to another instruction, to this instruction, to push program counter. Now what we're going to do, we are restoring back this number onto the top of the stack. So we're going to change this value. Okay, you see? And then we are popping the top element of the stack into the program counter. So we are branching back, you see here, to this instruction. So if I press enter, we are always repeating this loop. Done.